Okay, so now let's look at another hash function, which is called Whirlpool. And let's get the annotation. So as before, we want to know it has the same structure as SHA-512. So we want to know how to pad. We know, okay, padding. And initial value is 0. And we want to know the compression function f. And in this case, unlike SHA-512, that f is not invertible. In this case, this f is actually an encryption. So this is an encryption algorithm. So this is AES-like encryption, which means that it's going to be on finite fields. On a finite field. Okay, so we have seen AES, so this will just be similar. All right, so that's what we are going to look at. Remove this. Okay, so padding. So first, okay, bring up. So remember in SHA-512, okay, the input length is up to 2 to the 128 minus 1. So in this case, it's it takes a square, so which is 200, which is 2 to the 256 power minus 1. But the output is still the same length. Okay, so output still the same. So small gamma is still 512. So the padding is similar. Okay, just similar to SHA-512. You first take the length, first write the length of M, that's capital L, into a 256 binary bit. Okay, then you put it at the end. Separate between M and this, and also you want something that's separable. So to fill in, right? So you want something to fill in the middle. That's 1, 0. So this to the L's. So which means that you got L many zeros, and L is defined by this number. So the purpose now is to make sure the padded string is divisible. The length of it is divisible by 512. Okay, so now you, for this padded string M prime, you write it into a sequence of blocks such that each block is exactly 512 bits long. Okay, so you have n blocks. So that's padding. All right, so next we are going to look at the compression function f. Okay, so as we said earlier, this compression takes is an encryption. So you can think of it. So it's still the input is mi. You think of hi minus 1 as your key, and then it generates a ciphertext, and that's your hi. So this is your f, and f so f actually is a encryption, which is wxk exclusive or x. So which is so that means a little bit. So it's mi. So this is w. So let me. But you can think of that as a w, but it's just a little bit. So this is a w, and then this one, whatever the output here, you are going to do a exclusive OR. Okay, and that's your hi. So then this whole thing is your f. Okay, so f is this. So now we just need to look at w. So w is an AES-like encryption algorithm. So the block size is 512 bits long block size. The output is also 512 bits. So AES only takes 128-bit block size. Okay, so this is different. So now you look at this. The initial value is simple. It's just all zeros. Okay, and then hi is equal to hi minus 1, exclusive OR fmi hi minus 1. So that means you got a, so this exclusive OR, and you got the hi. So how, this is how Whirlpool is done. So now let's look at what this W looks like. Let me erase this now. All right. Okay, so W. Okay, so the number of rounds, now this is encryption, so it takes a few rounds, and the number of rounds is 11. So 11 rounds. Okay. It needs 11 round keys. Then we call it K0 up to K10, and the first K0 is K, and then you need to generate K1 up to K10 using the same sequence of 4 operations. So you get substitute bytes, shift columns, mix rows, add round keys. So that's, so this is how you generate K sub I. Okay. Here, RC sub I is a constant. Okay. They have a X box you can get, so which is defined here. All right. So let me move on. And the substitute bytes. Okay, so you got a 16 by 16 X box. which you can find from your textbook. Okay, and then now we write each 512-bit block into a 8x8 state matrix. Okay, so state 8x8 state matrix of bytes. Okay, so that means in order, so this is a byte. Okay, so this is X is a byte. In order to look at substitution, we are going to look at the first 4 bits as your row number, and the second 4 as your column number. And that's how you look at you do a table lookup of this X box and get the substitution value. Okay, so that's straightforward. And then shift columns. Remember in AES, we have a shift rows, but now we do shift columns, which is similar to shift rows, except that the columns rather than the rows are shifted. And it is a circularly shifted down J bytes, J from 0 to 7. So which means the leftmost column is not shifting. Okay, so that's simple to understand these two operations. Next, how about mixed rows? So mixed rows uses a matrix that's similar to mixed columns. So this is a matrix, and then mixed row is a multiplication of the input A of this matrix. Okay, so that's how it is defined right here. All right, so let me right here. Okay, and add round key is straightforward. Okay, so you just exclusive or 2 state matrices. Okay, A is represented as a state matrix, and the key case by the round key is also represented by a state matrix, and you just do a element-wise exclusive OR. Okay, so now the encryption structure is as follows. We write an input block as an 8x8 state matrix of bytes. Okay, and then so that will be your A0, and then so the input is A0, and then you do this operation. Okay, substitute bytes of AI, so starting from 0, right? So that means I want to do A1, A2 up to A10. So for AI minus 1, you do substitution by shift rows, shift columns, mix rows, and add round key. So this is the ith round key. Then you get AI, then your output is A10. Okay, so this is the diagram of this encryption algorithm. Okay, so on AES, each round, they have exactly the same sequence of operations. In encryption and decryption, it sorry, we didn't have the decryption block here, but this is a key. So the right-hand side generates 11 round keys, okay? So, but this part, each of these round follows the same sequence of operation. So this is key, round key generation. Okay. So that is Whirlpool.